Okay, so I'm gonna kind of start talking through this stuff. So we're gonna kind of transition over to some stuff with functions. Eventually we'll get to like function notation and that kind of thing, but we'll just start off with functions for now. So some different things here. Vocab, relation. You probably heard of this before, but relation is just any set of ordered pairs. It could be a graph, because we know graphs are sets of ordered pairs. It could be a table, or it could just be a bunch of ordered pairs listed out. In those relations, whatever, so this is supposed to represent like an ordered pair like x, comma, y. The first thing listed is going to be your independent variable, and then the second thing listed in your ordered pair is the dependent variable. Next thing, their function, and they do it in terms of like ordered pairs. So it says a function is a set of ordered pairs x, y, in which each first component x is paired with exactly one second component y. So what that would look like, say I made a couple little tables here. I'll give you one that works and one that doesn't work. So if I go x, y, something that would work where each x only has one y. Say I make all those x values different and then all my y values that pair with them different. So like each of those is a different order pair. What wouldn't work is if I say have like a 1, I'll just go 4 again, and then maybe I have like 2, 5 again, but then say maybe I go back to 1, and now my 1 matches with 7. Now that doesn't work. Okay, so if your x's are repeated here and they don't match with the same exact thing, then that would be no. If they're all different here, then we're good. Okay, and hopefully that's familiar from previous classes. Domain and range, again, those should be familiar from previous classes. So domain, all of your x values or independence, and then your range, all of your y values or your dependents. And then that other one there, they just give functions in a different form. So a function is the correspondence between two sets A and B, in which each element of A corresponds to exactly 1 and B. Same thing, but just instead of using ordered pairs, they're just saying groups of numbers or sets of numbers, but they mean the same thing. Real functions then, so domain and range are both sets of real numbers. And then that symbols chart there, I never use really any of these except for the one that's like the real numbers one, which we do like that. I have no idea how to even write the like z for integers. I don't know if you're supposed to like do it like that, or I don't know. I don't know how they actually do those. If you just put like a z, that would be fine if they say something with integers, or a q for rational and an n for natural numbers. That's how I know they do the one for real numbers, but I don't remember really ever using the other ones too much, so I'm not 100% how to write those, but if you just use those letters, that's fine. And then something that's probably new, you guys have never seen something like this before, have you? So this is kind of a new thing. So it just means member, and it's just an element of that set. So what it's saying here, so if x is in that set, so if x is something in the set, usually they'll use like real numbers or something like that. They're just saying whatever value that is in that group. So like x is in the group of real numbers or something like that. And we'll do some examples later with that. And yeah, so we'll jump to our example sheet then. So it should have a new packet there. So grab that. And first one there, we got a club at a high school, needs t-shirts for their upcoming tournaments. They were able to negotiate a buy two, get one free deal from the store. Cost for one shirt's $10, and the first thing we're supposed to figure out is which of these statements is true. Is the cost C a function of T, or is the number T a function of C? Okay, so my first thought here is I should probably figure out like how much money and what the t-shirts and stuff is going to cost. So I'm just going to, this isn't part of the question, but I'm just going to do this for kind of a visual. I'm going to make my own little kind of table here. Which of those, well, I guess that's the next question. Which one's independent and which is dependent? Which of them do you think is the independent? So which one would we have to know first? How many t-shirts or what the cost is? How many t-shirts, right? Because we have no idea what the cost is unless we know how many t-shirts, right? So my t-shirts would be in the independent spot, or like the x spot, and then the cost would be in the y spot because that's the dependent, what we get kicked out. So if I buy one t-shirt, how much is that going to cost me? $10, right? Okay. If I buy two t-shirts, 20. If I buy 3, 20 again, right? Because if we buy 2, we get 1 free, so we still only have to pay $20 there, and we would get 3. What about 4? 30, because we would get our 3 for 20 bucks, but then now we're getting a fourth one, so we have to pay an extra 10 bucks there. So 30, and it would just kind of keep going from there. 40 would be the next one, and then it would drop back to 40, and so on there. Okay. So now what we want to look at here is we want to figure out, okay, which statement is true? Is the cost C a function of T, or is the number T t-shirts a function of C? What you're always looking for with these is you're always looking at the second letter. So like in this case, T is our second letter. In this case, C is the second letter. We don't want that number to be repeated. Okay, so looking at the first one, the cost C of a function is the number of t-shirts. We're looking there to see if any of our t values would ever be the same. So would any of those t values ever be the same and kick out a different number over here? No, they wouldn't. Now, if I went with the opposite way with that, the cost C, as my thing I'm looking for repeats for, did any of those repeat? Yeah, they sure did. So is that one going to work if they repeat? No, they do not. So that's not the one that works because that C is the thing that's being repeated. So it's that first one that works. So it's the cost, what's it say? The cost C is a function of the number T of t-shirts. And if you want to write a little note to yourself here, like you could write like second letter can't repeat. I think that's the easiest way to remember that kind of stuff, because this function stuff, like, is it a function of this, is it a function of that, it's so confusing. Like, I always get myself tripped up. But if you always look at whatever the second thing is, so like in this one, t-shirts was the second thing listed, that one cost was the second thing listed. If you look to see if that repeats, it should always follow that pattern. Does that kind of make a little sense? Those are kind of tricky. Okay, so now B, we talked about this a little bit before, identifier independent and dependent. So independent, what did we decide for independent? The T, right? Because that was our t-shirts, because our number of t-shirts is going to tell us, the cost depends on the number of t-shirts. That's why that's the dependent one. But yeah, that's the one that we have to start with, and then it's going to kick that out. Dependent's always what it kicks out. Okay, and then now we got to get into domain and range here. Domain is that X or Y's. The X's, so in this case, our X's is like our t-shirts, right? So for our domain, what do you think are possible values that could be in for those t-shirts? Okay, integers. Okay, why would we want integers versus like real numbers? Yeah, we don't have parts of t-shirts, right? Are we ever going to have like a 3/4 of a t-shirt we're selling? No, that would be silly, right? So it can only be like the regular numbers. What about positive versus negative? Always positive, right? Because we're never going to have any negatives, right? So what I would write here is I would write non-negative integers. And I would write non-negative versus positive, because, or I write this instead of positive because if I just put positive, does 0 count in the positive numbers? No, it does not. Does 0 count in non-negative numbers? Yes, it would. And couldn't we order 0 t-shirts? We could. It would be silly to order 0 of something, but that's still a possibility that you could have 0 of it. Does that kind of make sense? Okay, so now our range then, what types of numbers are we always kicking out? Okay, so we got the positives again. Again, I'm going to go non-negative because if you plugged in 0, you would kick out as 0, right? So I'm going to go non-negative again. So agreed there. Are we ever going to have decimals with any of that stuff? We won't, right? So even though it's dollar amounts and we could have decimals, if this is just going by tens here, are we ever going to have decimals? Nope, so I would just say integers again. And then more specifically, what are all of those numbers always going to be? Multiples of 10, right? Because if each shirt, of course it does that, if each shirt is 10 bucks and it's not like we're getting any discounts or anything along the way, it's always going to be counting by 10. So you could also put like just like comma, multiples of 10, because it's always going to count by 10. Okay, and I think we're back to the sheet. Nope, example 2. So we'll go flip to example 2, and I think, yeah, this goes right along with that one we were just doing. I should have probably put them on the same page so you could read them both, but we'll go with it. So consider cost of buying t-shirts given that example. List the ordered pairs of the function for values of t 1 through 10. Okay, so if we're listing ordered pairs here, First one would be like one t-shirt. What did it cost for one t-shirt? $10. Two t-shirts, 20. Three t-shirts, 20 as well, right? Because it was buy two, get one free, so also 20. 4, 30, 5, 40. So that would be another two that we just bought. So the sixth one would then be, it would also be 40 because we'd be getting that next one free. The sixth one would be free. And then 7, 50 because we got two free so far, but we're still paying for the rest. To jump down a line here, 8, 60, 9, 60 as well because we're getting that third one free again. So like every third one we get free. And then 10, 70. Yep. Okay, for B, they want us to graph it, so I'm just going to sketch out a little graph here. And we only have to have the first quadrant because it's all positive stuff. Which one's going to go across the bottom? Is that shirts or cost? The shirts are independent, always goes across the bottom. So number of t-shirts, and then we could label that as RT there. And then up the side then would be our cost, and you could put that that's in dollars. And then up the side that would be our C. Okay, and then we're going up to 10 for shirts, right? So I probably didn't need to make that line so big, but whatever. And then we got to go up to 70 on the side. You want to just count by 10s to keep it easy. Just go up to at least 70 there. That's our highest one. And then once you get that, then you just graph those points. Okay, and our graph kind of makes sense there because obviously we're going uphill. Our cost of our shirts is just going to kind of keep going up the more shirts we get. But you can kind of see those little leveling off spots there. So like the 2 and the 3 are at the same height because 2 t-shirts and 3 t-shirts cost us the same as 5 and 6, and then 8 and 9, and that'll always happen on those multiples of 3, right? So if we buy 2, we get 1 free. That would be our setup. Okay, now we're back to our example sheet here. Let's do all of these things. So piecewise there, look that up. I would go to the back for that one because there's a better definition in the back for piecewise. That's just an example of a piecewise function if you're not sure what they actually look like. And then we'll do that example. And I would sketch these little pictures of the vertical line test thing, and then we'll talk through that. You don't have to do anything fancy if you just do, a little graph like that and something like that. That'd be good enough for your little graphs. They don't have to be anything specific. Okay, so first thing there, that piecewise stuff, this should have been something hopefully I'm sure you talked about in Algebra 2 last year, but it's kind of like combining multiple functions into the same kind of grouping. So it says definition of a function whose domain is broken into subsets with a rule for each of the subsets. So this is just kind of an example of that where they'll have like two separate like equations here or functions. And then with each of them you just have some sort of rule here. So like if your n that you plug in is an even number, you use that one. If your n you plug in is an odd number, you use that one. That's just a random example. Sometimes it'll be like if your n is greater than 0, you use this equation. If it's less than or equal to 0, you use the other one. I'm going to jump down to vertical line test and then we'll go back to that example. So vertical line test is another way to see if something's a function. So in this case, this normal parabola would be a function. Have you heard of vertical line test before? Where you basically take like a pen or something and you go across and you're looking for to see if your pen touches that graph in more places or more than one place at a time. So like as you go across there, it's only touching in one spot at a time, so that's a function. But as we go across here, it's touching like the top of it and the bottom of it at the same time, so that would not be a function. Okay, so hopefully that's a review for you guys. Okay, back to our example sheet. We'll go to example 3. Here they want us to find the domain and range of the function with that rule. So what I would do, since I have no idea what that looks like, I would just go to my calculator and type that in. So go to like my y equals, and then just straight up type that in there. So 3 parentheses x minus 5 to the power of 2, and then minus 1. And then to get a visual of that, I just hit my graph. And I get something like that. So now what we want to do here, I'll just do a little sketch of it on this. This is our graph. We've got to figure out the domain, which would be like this way with it, so how far it's going that way, and then also the range, which would be like top to bottom, okay? So domain-wise, are there any limitations or things that wouldn't work for our domain going out there? Not for the domain, because if we keep going here, won't that just keep getting wider and wider? That's a horrible picture, but won't it just keep getting wider and wider and wider and could pass into the negatives? So nothing with that. Are there any limitations on it? There wouldn't be, right? So if there's no limitations on it, what do you think are numbers that could work for that x value? All what? All real numbers, right? Because couldn't we plug anything in there and it would just kind of keep spreading out there? Yeah, so for our domain, what I would do is our domain is the set of, usually they'll use the curly brackets when it's a set. It's our x values that we're looking at, and then they just put a line there. I don't know why. And then this is where I would use that element thing, where it's your x is an element or a member of the set of all real numbers. So that's that weird little e symbol that we wrote down before. So that's just saying x is an element of that set. So x is in the set of all real numbers. Okay, and then domain-wise, or not domain-wise, range-wise, now we're going with our y's. So now here, we're going bottom to top there. Would there be any limitations there of numbers that wouldn't work? Yes, there would be, right? Because wouldn't it kind of cut off right there and we couldn't do anything below that? Yeah, so if that cuts off right there and we can't go below that, it would just be numbers bigger than that for our range, right? How do we find where that is? Yeah, we could do that, yeah. So to get it specific, so you can either go trace and try to get close, or do you guys know you can actually find the minimum? So to find the minimum, you go second in that trace button, minimum, and then when it says left bound and right bound, you just want your little cursor to be on the left and right side of it. So left bound there, on the other side, right bound, enter, guess is dumb, and then it tells me that. Do you guys know that when it's like 4.999 like that they just mean 5, truthfully? Do you guys kind of know that? Sometimes the calculator can only think so hard, and it's supposed to actually be 5 and -1 there, but it can only really think so hard. So that would just be like the bottom of your graph would be at 5, -1. But really here, we only care about that -1 there, right? Because that would be the bottom of it. So how would we write this out if it's numbers that are bigger than -1?
Y's greater than or
Absolutely, yep. So we'll go that same curly bracket there, the y, and then our line. And then this time, since we've got some limitations, it would be our y is greater than or equal to wherever it stops there, which is that -1. So you wouldn't need the element thing on that one because it's a little bit more specific. Okay. We're almost done. So just jot that for function notation quick, and then we just got that one example left, and we'll be done. Okay, we'll finish up this last example here, and then you guys can go to lunch. And just make sure when you do your assignment there, skip that whole group of them. So skip 4, 5, 14, and 17. They take a long time, and some of them aren't worth our time. So just skip those ones when we get to the assignment. But we'll do this last one quick, and then when we get finished, you can go to lunch. Okay, so here they give us this function. You guys have seen function notation before, right? Where this doesn't mean multiply, it just means, oops, let me try to zoom out. It just means g of t, where that's kind of like our x value, and then this whole thing together is kind of like our y value. So here, what I would do to evaluate these, you can either just take those numbers and put them into those spots. So you could go like 2 times -2 squared minus 3 times -2 minus 2 to get what that is. Or, since we have to do a whole bunch of these, wouldn't it be easier to maybe use our calculators? Yeah, so what you can also do here is you can type this into the y equals of your calculator. So like 2x to the power of 2 minus 3x minus 2. And then if you go, you can either go on the table and look for them, or if you need some specific ones, you can go on the graph. You guys probably have used this before, where you go second trace button and calculate to find a specific value. You guys done that before? So if you hit value, it'll say like x equals there. Well, aren't all of those values kind of like x's? Yeah, so you can just go there, and if you need to find -2, you just type -2, enter, and it kicks out your y. So like for part A, g of -2 would be 12. And then you just do the same thing with g of 3. You just do your value thing again, put a 3 in there, enter, kicks out that our number there is 7. So if I plugged in the 3 for all those x's, or t's in this case, it'd give me 7. And then same with the last one, I'll just tell you it should be 63. You do that. So now here it wants to know, does g of -2 minus g of 3 equal if it's in parentheses like that? So if I did my g of -2, that equaled 12, minus my g of 3 was 7, and they want to know if that equals. Here, if it's g of -2 minus 3, always do what's in the parentheses first. So if I do -2 minus 3, I'd have -5. So really they're asking me if it's the same as g of -5, which was 63. So would 12 minus 7 be equal to 63? No, it wouldn't, right? Because 5 wouldn't be equal to 63. So no, it wouldn't work like that. And then the last one there, when they want us to evaluate and it's got some other letter in it, you do actually have to physically plug it into the original function there. You can't do those ones on the calculator, but you would just take that chunk there that they give you and put it in for all the spots of the t. So you would go like, so if it's g of 3p plus 1 is equal to 2, instead of the t squared, you would do 3p plus 1 squared minus 3, and then instead of the t again, 3p plus 1 minus 2, and then you'd solve that out. FOIL, remember FOIL? So you'd have to FOIL this, because it'd be 3p plus 1 squared. I'm trying to go quick, sorry. So FOIL, that'd be 9p squared. Outside would be, you want me to just write you the answer and give you that so you can go to lunch? Okay, I'll just write the answer for you so you can go to lunch. If we need to talk more about this tomorrow because I went too quick, we can. But I don't want to cut into your lunchtime. So that's the answer. I'll finish it off and scan it for the online notes so you can see that. But I'll let you guys go to lunch. I don't want you to be too far behind. So